All right. Good evening. I hope I'm audible. So, um looks like we have only. Looks like we do not have any audience today also, but that is fine. Uh, what I'm going to do today is I gone through the assignments of this week, and it looks like all the assignments are pretty much easier for you to solve, and so I'm actually going to I'm not going to solve any same kind of questions again because that questions have been already solved in the lecture. And if you have any questions regarding that, you can post your questions in the common forum, and you can ask about it. I will be happy to answer it. But today we are not going to solve such kind of questions. Instead, we are going to focus on something which has a practical application uh, using chemical kinetics. So, what I have today is uh, I am going to talk about something called NOx emissions, which is very much crucial. Let's say if you are operating a gas turbine engine or a gas turbine in the sense rocket engines or aircraft engines. Okay, um, because aircraft is going to fly at high altitudes, it should not emit a certain gases which is harmful to the environment, and if it emits, it leads to global warming. So basically, if it releases greenhouse gases, it will lead to global warming. So the main ingredient or the important gases which constitute for global warming at that altitude is includes uh, carbon dioxide, carbon monoxide, and NOx, nitrogen oxides. In addition, there is ozone also, which also contributes to the global warming. But these are the main gases which contributes to the global warming, and there is a certain limitations, certain regulations set by the aircrafts authority. They used to say that if I'm using such engines, then my emissions, I should have a certain I should emit only a certain amount. Above that, it is not allowed. So there is some certain allowable emission norms which you should actually follow in order to operate such aircraft engines. Okay, and so that emission, how do we meet it? Because all these are due to combustion of fuel and air within the combustor, and it is expanding in the turbine and eventually in nozzle, and the gases are coming out. And if you want to control the amount of carbon dioxide, amount of nitrogen oxides at the exit of the nozzle or at the exit of the engine, you have to know what happens inside the combustion chamber. You have to know what is the what is this combustion process gives, what is the amount of these gases uh, comes out as a product of combustion. So this will directly correlate to the emissions. So uh, here what we are going to do today is we are going to analyze one such gas, which is NOx, nitric oxides. It can be NO2, lot of gases which comes under NOx. So today we are going to talk about only NO. Okay, and uh, uh, in this particular question, what we are going to do is we are trying to quantify what would be the emissions, what would be the NO concentration of NO or the amount of NO which is going to come out of the engine. But by using the knowledge we gained in this week's lecture. So in this week's lecture, we gone through chemical kinetics. We gone through different mechanisms for NOx formation. We gone through certain approximations we did, like steady state approximation, partial equilibrium approximation, in order to arrive at uh, a good estimate of, let's say, mechanism, good estimate of the amount of NOx formed, not even not just NOx, amount of products formed. right? And we also gone through the rate laws, the how do we write the time evolution of these concentration of these gases, and how these things are correlated is what we studied in this week's lecture. So we are going to use all this knowledge and we are going to apply it to a gas turbine engine, and we are going to find out whether what kind of operating conditions I should follow in order to meet a certain emission regulations. So let's just quickly go through the question. So I actually gave you a rough idea. If we go through the questions, you will come to know, you will get a full idea of what we are going to do today. So as I said, it's going to be based on NOx emission, and um, here what I'm going to do, I'm considering only the Zeldovich mechanism. So same such kind of analysis what we are going to do today, you can do it for other systems, other mechanisms also, for other gases also, and you can come up with a good estimate. So today I am going to consider Zeldovich mechanism, and we know that Zeldovich mechanism is for formation of NO, and this is the Zeldovich mechanism. We all know that, and there is this. So initially there will be a oxygen atom and a nitrogen atom, which forms NO and N, and this N formed N will actually react with another some other O2 present in the mixture, and it forms another NO and an oxygen atom, and this oxygen atom again goes through this. So this is actually a cycle. So this will lead to this and this will lead to this. So it is like a this kind of loop keeps on going, and in addition there will be some other thing, there will be terminations, wall termination, there will be gas termination in order to stop this kind of things. Or it also depends on this kf. K is dependent on temperature. If the temperature is high enough, we know Zeldovich mechanism is for high temperature. It's actually high temperature mechanism. At high temperatures only you will observe such kind of mechanism. So the formation of NO is going to depend on K1, K2, and the concentration of O and N2. O, N2, and we have the rates K1 and K2, forward reaction rates for these two reactions. What we should find is we should identify the rate limiting step, which means which is the step is going to take a lot of time, which is the step is going to determine how much amount of NOx is formed. So is this step is going to determine the amount of NO formed, or is this step going to depend on, it's going to tell, or it's going to hugely depend on the formation of NO. So that we are going to find out, and then you should consider a global reaction. So this is the mechanism. This is the mechanism how it is, how in reality it's going to react. But we have a but we have the habit of writing a global reaction, right? And we also associate a global reaction rate to it. So what we do is we will again do a same thing here. We will write a global reaction for this mechanism, and we will derive an expression for the rate of NO formation using that global reaction mechanism, and that is going to depend on, yeah, K1, K2, N2, and O2. Okay, because at the end of the day you have N2 and O2, and that is going to through some mechanism and it is going to form NO. So if the gases have N2 and O2 separately, there is no problem, there is no emissions, there is no formation of NO. But the problem is these N2 and O2 is going to react with each other and it is going to give NO. So that is the problem, and that is what we are going to we are trying to quantify it. Okay, and the question is to consider a propane fired gas turbine combustor, so which is usually the aircraft engine gas turbine combustor operating at 1 atmosphere. For example, here we are going to choose 1 atmospheric pressure. Assuming that combustion reaction occur at much rapidly than the NO formation reaction, so we are going to assume that combustion is complete, which means I have propane, I converted everything into carbon dioxide and H2O. That is complete, which means that that has been completed, but NO hasn't formed. So from there NO is going to form. That is the assumption here we are talking about. Assuming that combustion reaction occur at much rapidly than NO formation reactions. So before forming NO, combustion is already been completed, or combustion is very rapid, so that you no need to worry about it. The major species concentration and temperature remain approximately constant after the fuel is burned. That is also one of the assumptions you are going to make, which means the concentration of CO2, since we are burning propane and it's aircraft engine, so fuel oxidizer is going to be air, which we are going to, right? And since we are doing something like that, the major species formed would be CO2, carbon dioxide, there will be water vapor, and there will be, if there is excess oxygen, there will be oxygen. If there is since air has nitrogen, nitrogen will be present. And this nitrogen and oxygen is what going to form NO. So that is what we are going to quantify. So other than these, all others are going to remain constant is what one of the assumptions we are taking here. And fuel is burned, which is when Zeldovich mechanism is active. So that is when Zeldovich mechanism is active, and we are going to apply our analysis only in that uh, you know, range, or only in those regions. Okay. If the resident time of the gas mixture in the gas turbine is 10 milliseconds, and if the regulation, so there is a typo, this is if the regulation limit NOx emissions to be 30 ppm by volume, which means parts per million by volume, what equivalence ratio will NOx emission regulations meet? Okay, so what I'm telling is, you have a gas turbine here. Okay, here we have a gas turbine and air is coming in. Okay, and it is going through a series of compression in the compressor, and then it's going to going through combustion in the combustor, and it is expanding in the turbine, and finally through the nozzle, and then it goes out. So the time it requires to go through all these things is just 10 millisecond is what I'm telling. So residence time of gas mixture in gas turbine combustor. Okay, so just the gas turbine combustor. So time. So if you let's say this is T1 and the time it goes out is T2. This T2 minus T1 is actually equal to 10 milliseconds. So this is the amount of time the gas mixture will stay inside the combustor. After that, it goes out of the combustor. So that is one of the uh, it's not an assumptions, it's like one of the crude calculations you can make, because you will be taking in air at very high speed, right? So you will probably run your engine at Mach point 0.8 or point 0.9. So if the engine is at or the aircraft will usually move at Mach point 0.8, which is around 280 meters per second or something. Okay, 280 or let's say 250 meters per second. This is the rate at which air is entering the engine, aircraft engine, and combustion chamber is going to be just, let's say, um, it's going to be 1 meter or 2 meters. So let's say if you divide that, so 250 divided by 2 meters, so it's you are going to end up having some point 0.1 seconds or something. So 0.01 seconds or something, which is around 10 milliseconds. So it's a crude estimate of how much what is the amount of time the gas spent inside the combustor is what we are telling. So that is given 10 milliseconds. And if this is the emission norms set by the officials, like set by the, so the environmentalists, they will see that you need to reduce your NOx emission to this much level, like all the engines should meet that requirements, and that emission norms is 30 parts per million by volume, which means nothing but uh, uh, based on volume, amount of volume, 30 parts per million is only NOx is allowed. So at which equivalence ratio you would expect this emission, so that you can run your engine at that equivalence ratio. Okay, so equivalence ratio is nothing but the mass of fuel by mass of sorry uh, fuel air ratio, actual fuel air ratio divided by stoichiometric fuel air ratio, right? So that is the equivalence ratio, with which equivalence ratio you have to run your engine in order to meet this NOx emission is what we are going to do. Okay, so provided that the problem statement is clear, first let's try to uh, identify the rate limiting step, because that is important and all your calculation is going to depend on only on that rate limiting step. Rate limiting step, in the sense, this is the main step which is going to take much of a time. If this step doesn't happen, the other subsequent steps will not happen. Okay, the other subsequent steps are very fast, and you can assume that it can, once the something is formed, it will automatically gets consumed. So that kind of steps are other steps. The steps which is taking longer time, the steps which is more important, is what we call as rate limiting step. So now we have two steps. Let's try to find out that. Let me write it down separately here. So first we have Zeldovich mechanism, and we have plus into K1F NO plus N. Okay. The second step is I guess it's N plus O2 K2F NO plus O. Okay, this is the first let's say first step. This is the second step. So now we need to find which one is rate limiting. Okay, so to find out that, we need to understand what is the um time required for NO to form through step 1. What is the time required for NO to form through step 2? So that can be, we can get a easy estimate by finding the characteristic time scales. So all these are bimolecular reactions, and we already know what is the characteristic time scale of a bimolecular reaction. So we know that tau chemical, let's say tau chemical is going to be, for a bimolecular reaction, is going to be ln of E plus 1 minus E in A, concentration of A times by concentration of B, whole divided by K of that reaction. So bimolecular reaction times B of 0 times A of 0. Okay. Now we also know that if concentration of B is very high, right? So let's say if concentration of B is very high compared to A. So this is basically what I'm trying to say is A plus B gives C plus D. And we are actually, for this reaction, what is the chemical time scale is what we are finding it. So if the concentration of B here, if the concentration of B here is larger compared to A, which is usually the case in our mechanism also, concentration of, so N2 is only going to form, O2 is going to form, and that is going to react to form NO. So we initially we have N2 and O2 as a major compound. Let's say in air also, N2 and O2 are the major components, major constituents of air gas mixture. O and N are very less in concentration. So we can say that for our case also this is true. So if that is the case, this tau chemical reduces to, so this reduces to simply 1 divided by K bimolecular concentration of B. Okay, so basically we already discussed this in lecture. That's why I'm not deriving it here. But if you have any doubts in derivation of this, please go through the lectures once again. Uh, and if you still had doubts, you please post it in the forum. We'll be able to help you. Okay. Now, this is the characteristic time scale. So, what is the time scale for each and every reaction is what we are going to find out. So, the B naught. So basically, let's write it for first reaction. For reaction one, this B is going to be nothing but N2, nitrogen concentration, and for second reaction, this B is going to be nothing but O2, concentration of O2. So what is the most easiest way for NO to form is what we are finding it, or what is the toughest way. So let's say for reaction one, let's find for reaction one. Um, For reaction 1, let's say I denote it as tau C1 is going to be 1 divided by K1F forward reaction times the concentration of N2, right? So this is the characteristic time scale for the first reaction, and let's put it's also given that K1F is this big expression, right? So let's substitute that also here. 1 divided by 1 point into 10 power, I guess it's 10, 10 power 14, 3870 by t. So it's 10 power 14 into exponential of minus 38370 by t. So it's going to depend on temperature also, and we have concentration of N2. Okay, now let's write for reaction 2 also. So tau C2 is going to be 1 divided by K2F times concentration of O2, which you can similarly write it as 1.8 into 10 power 10 exponential of this K2 here, 0.8 into 10 power 10. There is T also here, exponential of minus 4680 by T. Minus 4680 by T. There is one more T here. Times the concentration of O2. Please remember this is in centimeter cube per gram mole second. Centimeter cube per second. So which means concentration also you may need to substitute in terms of gram mole. Uh, how do you substitute concentration? It is going to be um, per unit. Yeah, so it is going to be gram mole per centimeter cube, right? So concentration in terms of volume, so it's going to be moles per centimeter cube. So this should be substituted in moles per centimeter cube. Please remember that. You will get 1 divided by second. You will get, so the time scale is in terms of seconds. So it will be, the whole thing will be in terms of seconds. Okay, so which one would be which one will take longer time for it to work? So that is what we are going to see. because that is going to determine whether NO will form or not. Okay, so if the first one takes longer time, so that would be the rate limiting step, because the first one has to produce N, which is used by the second. So once N is produced, the second can easily form. Or if the second is taking longer time, so NO will automatically form with a very high rate. So half of NO would be very highly formed. So that is what it means. So we need to know which one is going to take larger time. So let's say, for example, we will say, for example, I'm going to take, what should we take? It is going to depend on temperature. Let's say for a temperature of 1500 Kelvin. So that is usually everywhere. Alright. So if the temperature is 1500 Kelvin, and let's say if you assume that concentration of N2 and O2 is 1, let's say, for example. So, so we are just trying to find out which is the important reaction. That's why assuming N2 and O2 concentration is just simply 1 gram per centimeter cube. So gram mole and moles both are same actually. Now let's say if I substitute it, let me find out an order of magnitude for TC1. TC1, let's say if I substitute it in here, calculate it. So I have 1500 Kelvin, so 38370 divided by 1500. Um, exponential minus 1.82 into 10 power 14. Okay, and 1 divided by answer. So tau C1 is coming out to be 7.066 into 10 power minus 4 seconds. And now let's find tau C2. Tau C2 is coming out to be 680 divided by 1500. Instead of minus answer to 1.10. So tau C2 is coming out to be 8.38 into 10 power minus 13 seconds. So from here what you can find is, this is for just um, an arbitrary case, right? So even if N2 and O2 are very large differences, let's say even if N2 is 1 and O2 is 1000, right? Or if N2 is 1000 and O2 is 1, right? Even if that is the case, it, this is more likely that TC1 is always going to be greater than TC2. The reason is around how much orders, so around uh, orders different in magnitude. So which tells that, so let's say if it takes how do you say, zero point 0.7 milliseconds for me to form NO and N, within the next nanosecond or femtosecond, I can simply form another NO, because N is there, O2 is there. N and O2, the second reaction is going to be very fast. So basically, since time scale for 1 is greater, that is going to determine how much amount of NO is going to form. So as soon as one first reaction happens, the second reaction quickly happens. So that is the reason what your rate limiting step is going to be. Why do we say rate limiting step? The reason is, here we are interested in how much is the rate of the NO form, and which step is going to determine how much amount of rate? The first step, because that is taking longer time. So let's say if my gas stays 10 milliseconds, which step is going to determine the NO formation? It is not the second step, because second step needs N to form. So first step will take larger time and it also produces NO, right? So that's why the rate limiting step is going to be the first step. So the rate limiting step is the reaction 1 in this mechanism, which is N2 plus O gives NO plus N, K1F. It can also be noted that if you look at it, K1F is going to be smaller than K1F is very much less than K2F, at least by order of magnitude t. So there is an exponential factor also. So if you look at it, this is K1F and this is K2F, and the exponential, the pre-exponential factor, which is 1.8, is same both the side, but here you have 10 power 14, here you have 10 power 10, right? So, and here we have additional t. So if you look at it, the K2 is going to be just around, let's say, 10 power 13, and this is going to be around 10 power 14. In addition, here you have exponential terms. So this is, so until the exponential term, it is clear that K1F is going to be greater, right? Uh, Here you have division by t term. So when you divide it by here division, here you are going to be in the order of 1. But here when you divide it, you are going to be in the order of 2. And since it's exponential term, this will going to dominate over the other one. So that is the reason you can also, just by seeing at the rates, you can say that which one is higher. Okay, and the rate limiting step is what we call as and since rate of this is lower, the rate at which the reaction proceeds is lower here, that's why this first reaction is called as rate limiting step. You can argue in terms of characteristic time scale also, can argue in terms of rate also. Okay, so having understood that this is the rate limiting step, this is the step we have to worry about, and this is the step is going to come again and again in the subsequent questions also. So now we found the rate limiting step. Let's look at question 2. So what is the next step? You need to consider a global reaction and find the rate of NO formation. Now it's a real challenge. Now we need to, so we just found out that this reaction is responsible for NO formation, right? So this is the main reaction which is going to responsible for NO formation. Now we are going to find out that what is, how, now you are going to actually quantify what is the amount of NO formation. So for that, let's write a global reaction. I'm sure that you must have seen it in the lectures itself. So it's going to be just N2 plus O2. This can be just the algebraic sum of those two reactions in the reaction mechanism. Okay, and this is going to happen at some rate kg. Okay, and now let's say if I want to find out the rate at which this NO is formed, which you can write it as d by dt of NO concentration, is going to be nothing but this kg times the reactants times the product, and this concentration will have some factor in the power, but that power doesn't really lead, it's not actually the stoichiometric coefficient which is present here. So this is not 1 and 1, because for a global reaction this orders can be orders is not equivalent to stoichiometric coefficient, but in reaction mechanism you can simply write the stoichiometric coefficient over here and here. Okay, in a reaction mechanism means in each and every elementary reaction, but in a global reaction you should not write that, because uh, in real N2 is not going to just collide with O2 and just form 2N, so that is not going to happen. So it is going to happen through a series of elementary reactions. So elementary reactions, when you write a rate at which the each species vary, at that time for an elementary reactions you can write these stoichiometric coefficients over there, but in global reactions you should not write. Uh, Now we need to find m, n, and kg. Once we find these three, we can simply find the d by dt of no, right? So let me write that down. So now to find m, n, and kg. So how do we find this m, n, and kg? So that is going to be from our knowledge from the Zeldovich mechanism, right? So let's try to do that. So reaction one. So reaction one is what is reaction one? It's going to be O plus N2 gives NO plus N. This is the reaction one. So let's say if I write dNO by dt for this, what this is going to depend on is it's going to be uh, K1F concentration of N2 power 1 and concentration of O power 1. So that is true. But it's not just reaction 1. NO is formed through reaction 2 also. So it is going to be N plus O2 K2 plus O. So let's say for this, if I want to write formation of NO. So before we wrote for a global reaction. So for this, let's say if I write formation for formation of NO, we will get K1F times N2 concentration O concentration. So from first reaction plus K2F times N concentration and O2 concentration. Alright. So this is the contribution from first reaction. This is contribution from second reaction. So the question is, we have in the global reaction we have N2, we have O2. Okay, K1F and K2F is known, so that is not a problem. But how to deal with O concentration and N concentration? So that is the question we need to solve. So here we need to make certain approximations. That is what we studied. We studied that they can apply a steady state approximation. So for which species we can apply steady state approximation? Steady state in the sense the concentration of that species is going to remain same for you know throughout the throughout the reaction. Okay, so let's say, so maybe before doing that, let's intuitively try to understand how the concentration varies with respect to time. Okay, so this is the time and this is the concentrations. Okay, concentration of any species. So let me write it down like this. Now let's say for N2, so initially N2 will be at certain concentration, and as time goes we know that N2 is going to get consumed and forms NO. So N2 concentration is going to reduce. Similarly O2 is also will be at some place and it is also going to reduce and go to some other place. That is fine. Now NO formation. So this is N2, this is O2. Now let's draw for NO. So initially it will be 0 because it's not present, and as N2 and O2 is getting consumed, it is going to go higher and higher. Okay. and as it goes higher and higher, it is going to increase and then eventually reach a steady state or something. So this is going to be NO. Okay. Now, how about N and O? So here we have N. So if initially from the first reaction, what happens? N2 will collide with O. Okay. And so it forms N. Okay. So let's say it forms N. So as soon as it forms N, it's going to get consumed in the second reaction, because second reaction is very fast. It's in femtoseconds. So as soon as N forms, it's going to get increased. I mean, it's going to get uh, consumed for the second reaction. So what is going to happen is there will be a slight increase, okay, and then it is almost going to remain constant throughout, and at the end it may go to zero because all the reactions has happened. So this is going to be the profile for N, a time evolution of N. So through some initiation reaction which slightly increases the concentration of N, but we know second reaction is going to happen simultaneously. So N is going to keep on getting consumed. So since second reaction is very very high, so whatever N is going to form is going to get consumed easily. So the N's concentration is not going to change throughout your throughout the mechanism. Okay, so that is one thing we should note. And O concentration. O is also here, if we need, we require initial O. It is going to increase, and then O is responsible for forming N. Okay, and then so that is also almost is going to so that this is little bit trickier, but N is clear. So we can, O can be anyway, so it can be, so in addition there is also another problem. This O2 and O can uh, O2 can form 2O, 2O can again come back to O2. So that complication is here in terms of O and O2. So let's not worry about O2 here, O concentration of O, but the concept here, it should be clear that N is going to get consumed by the uh, through the second reaction. So because of that, the concentration of N is not going to vary much within the reaction. So if that is the case, this almost reach steady state, right? This is almost reached steady state. The concentration has reached steady state. So it is not changing anymore. So if that is the case, then let's say if I want to write a rate law for this N, okay, rate law for N, formation of N. So that is going to be equal to, from the first reaction, it is going to be positive. It's going to be, so this reaction is going to generate N, so it is going to be positive. K1F of NO and sorry, N2O. Okay, and now through the second reaction, what is going to happen is N is getting consumed, so there should be a negative sign K2F of N and O2. Okay, and what we saw is, we saw it's a steady state. Since it's in steady state, this is going to be equal to 0. Okay, which means we are applying steady state approximation, steady state, which means I'm applying steady state approximation for the species N. So this is an approximation in order to remove the dependence of N. If not, you won't be able to, come up with a good estimate of formation of N. Steady state approximation of concentration of N. Okay, so let's rearrange this, or rewrite this. K1F of N2 concentration, O concentration, is going to be equal to K2F of N and O2 concentration. So we are interested in finding the concentration of N. So let's rearrange in terms of N. N is going to be equal to simply K1F of N2 divided by K2F of O2. So now we somehow came up with the concentration of N. So only thing remaining is we need to come up with the concentration of O. So then we will be able to uh, find out the how the NO is going to vary, or how much NO is going to get produced. Okay. Now the second task is to find O, concentration of O. So what we said was find concentration of O. What we also know is we know that O2 we have here can dissociate, form 2O. Our two oxygen atoms can recombine to form O2. So that what you can say is you can say this reaction, if you assume it's really fast, assuming really fast, because that is also this assumption is not a bad assumption. The reason is we already saw that the formation of NO are very time consuming process. It is taking around a millisecond or so. Usually these reactions should happen very fast at around microseconds or nanoseconds, but this is taking longer time. So but this reaction O2 forming O or O forming O2 is going to be very fast, resuming really fast compared to other reactions in the sense the reaction 1 and reaction 2 in our uh, mechanism, Zeldovich mechanism, compared to reaction 1. So what you can do is you can say that this is at partial equilibrium. So that is the another approximation that we learnt in the lecture. This is a partial equilibrium approximation. So this approximation is for a reaction. So remember, steady state approximation is for a species, and partial equilibrium approximation is for a reaction which is really fast compared to the other reactions. Okay. So if this is the case, then we know that let's say if I want to write a equilibrium constant for this reaction, this is going to be nothing but simply PO. PO is partial pressure of oxygen atom divided by, there's going to be P naught. So let me write it above. Okay, times 2. This is the product divided by P of O2 by P naught is the standard pressure. Uh, that's all. And say if I rearrange this, P of O by P of O2, P of O square into 1 divided by P naught, standard pressure. Standard pressure is 1 atmosphere. And I can also rewrite it in terms of mole fraction. Let's say if I write PO square is nothing but mole fraction of oxygen atom. So I'm denoting mole fraction as X here. Mole fraction of oxygen atoms times the pressure. Uh, so here it is going to be whole square, and P of O2 is going to be mole fraction of O2 times the pressure. Okay, so let's say if I substitute it here, so Kp is going to be mole fraction of O square divided by mole fraction of O2, and into P divided by P naught, and since P is equal to 1 atm, which is also equal to P naught, we can cancel this. Okay, and we can write Kp to be x of O square divided by x of O2. And what we also know that is, how do you find Kp? Kp is going to be simply exponential of minus delta G naught for that reaction divided by RT. So this we discussed in the last session also in the uh, you know also, right? So how do you find delta G naught? Delta G naught is going to be um, 2 times G of formation of O minus G of formation of O2. Since O2 is a naturally occurring element at 1 atmosphere, this is going to be equal to 0. So this is going to be simply 2 times G of formation of O, and that we know RT is in terms of temperature is going to be, so we need to find temperature in order to do that. So here what we found is we found that so finally we are interested in concentration of O, here in terms of mole fraction. So the mole fraction of O is going to be equal to fraction of O2 times Kp whole power 1 by 2. Okay, so this is how it is going to be depending on. So let's say if I want to write in terms of we wrote everything in terms of concentration. Let's say if I want to write in terms of concentration, then we know that PO is going to be concentration of O times RUT. So if you relate it to that, XO of P is equal to concentration of O times RUT. So X of O is nothing but concentration of O times RUT by P. Same with X of O2 is going to be concentration of O2 times RUT by P. P is the pressure of the mixture. Okay. And now let's say if I put it all together, concentration of O times RUT by P is equal to concentration of O2 power half into constant Kp times RUT by P whole power half. Okay. So if I rearrange this, I will get concentration of O to be equal to concentration of O2 power half times Kp into P by RUT. Right, because RUT by P, so if you divide it, you will get divide by RUT by P whole power half. So I wrote it reverse. So that's it. We found the concentration of O, we found the concentration of N. So to find concentration of N, we use steady state approximation. To find concentration of O, we used partial equilibrium approximation. And now it should be easier to find the substitute in this equation. Okay, so let me put some equation numbers over here. So this is equation, says this is equation 1. Okay, this is equation 2. Now let's substitute it in the equation 2. Substitute N and O in equation 2. So d by dt of NO is going to be equal to what it is going to be equal to K1F N2 into K1F N2 into concentration of O plus K2F O2 concentration into concentration of N. So instead of N, let's first substitute N. It's going to be K1 N2 into concentration O concentration divided by, so K1F O concentration divided by K2F times O2 concentration. Okay. So this and this, sorry, this and this gets cancelled. So if it gets cancelled, this is going to be simply 2 times K1F into concentration and O concentration. So as I said, this K2F was outside the picture. in the formation of NO, because simply because it's a very fast reaction, so that is not going to determine how much amount of NO is formed. So as soon as something is formed, it will just directly double it. That's it. Substitute O concentration here. O concentration is going to be is equal to 2 times K1F into N2 concentration times O2 concentration power of times Kp into P by RUT whole power of. Clear, right? So this is going to be d by dt of NO. So let me rewrite this again here. So d by dt of NO going to be equal to times K1F into Kp into P by RUT whole power of into N2 concentration power 1 and O2 concentration power half. And we also know from the global reaction, which is equation 1, d by dt of NO is going to be simply Kg into N2 concentration power M and O2 concentration power N. Okay, so if this is the case, then you can simply correlate these two to get Kg. Kg is going to be simply K1F times Kp P by RUT whole power of. Okay, and M is going to be equal to 1 and N is going to be equal to half. So as I said, M and N no more will be integers, and the order of this reaction is going to be 1.5, which is M plus N, right? 1.5. So your formation of NO is going to depend on N2 concentration. Formation of NO is going to depend on O2 concentration, and it is going to depend on temperature to the root. It's going to depend on K1F also. So these are the parameters. If you control it, you will be able to uh, properly limit your NO formation. So having said that, let's move on to third one. So you derived an expression for the rate. Now let's apply this expression for a real gas turbine combustor, so that we can, so it's like we can select which equivalence ratio we should run our gas turbine combustor in order to meet the requirements. Um, for that, what are the assumptions you are going to make? We are going to make assumptions. So before writing assumptions, let's try to write the equation for the propane fired combustor. Propane fired combustor is going to have C3H8 is the propane, and you are going to have R for different equivalence ratio. So let's write it in terms of equivalence ratio. So this is going to be R is nothing but O2 plus 3.76 N2. So now we need to write something here. We'll come to that. And this is going to react, and it is going to give me CO2. It is going to give me H2O. It is going to give me some O2 if I have if I have fuel uh, fuel lean conditions. Okay, which means oxidizer is more, so O2 will appear also. And in addition, let's say because of partial equilibrium between O2 and O, which can easily form, that is one of the assumptions we made. There will be some O also, and there will be N2. Okay, now these O2 N2 in addition to this O is going to form NO. So that we will find it now, but this is the this is the global reaction until NO formation. or until the combustion. Once the combustion is over, NO is going to form because of high temperature. That we are going to find out. So this is before NO formation. Okay. Let me try. Because NO formation requires N2 and O2, and now it is there. N2 and O2 is there. So we need to find out this factor. This factor is going to be, we already know, if it's a stoichiometric, this is going to be x plus y by 4 for any hydrocarbons. C3, which means CXHY. So for a given equivalence ratio, this is this factor A. Let's say, let's write it as what can we write this? We can write it as let's say Z. Okay. So this Z is going to be simply x plus y by 4 divided by the equivalence ratio, which for us is going to be 3 plus 8 by 4 divided by 5. You can actually do separate calculation. You no need to exactly follow. This is the method. This is how you find out for any hydrocarbon. Uh, if you do proper calculation itself, you will be end up getting this. So you will have 5 by 5. No, so nothing but, so it's nothing but z is equal to 5 by 5. So let me rewrite it here. It is going to be 5 by 5. So let's say if I have an equivalence ratio of 1, okay, stoichiometry. If it is a stoichiometry, the coefficient is going to be x plus y by 4, which is 5. So that is going to be there. If I have higher equivalence ratio, then I have lesser oxidizer than it required. So this whole thing will be lesser. If I have lower equivalence ratio, let's say less than 1, which means fuel lean condition, which means more oxidizer. So if I have 5 to be less than 1, this 5 by 5 is going to be more than 5. So that is fine. Now we found out. Now the thing is, we need to find A, and we have C, H, O, and N. Only 4 unknowns. Okay, for any 5. For with that we cannot find 5 unknowns. It is not possible because we have O2 and O. We could, if we want to find, then you have to have 4 atom balance equation, and as I said, we have to have a, you know, this equilibrium, the Kp equation for this O2 and O in order to find it. But solving that together is going to be different. So what we do is we will take help of NASA CEA. We will ask NASA CEA for these coefficients, and we will use it as a input to our whatever we developed here. Okay. So I will tell you about it. So now uh, let's try to find out how much NO is built up. So what they have said is the residence time of gas mixture is given. So let's say the residence time is tau residence. Okay. So tau residence is given. So we need to understand how much NO is formed during that residence time. So that will give us the idea of so because after that, after the combustor, your temperature is going to keep on decrease, and as temperature decreases, the Zeldovich mechanism is not going to happen. NO is not going to form. So only place where NO can form is at high temperature, and the high temperature is only present in the combustor. So let's say if we get a good estimate about NO formation within the combustor, that is most probably is going to be at the exit of the engine. Okay, so we already found out that concentration d by dt of NO is nothing but kg times N2 plus O2 power 1 by 2. Okay, this is what we found. So now what we will do is we will differentiate this. Sorry, we will integrate it for a time. So this is a time derivative. So we can take the side, and we can integrate it for residence time. Okay, so times dt. So we will integrate from 0 to t tau residence. Okay, similarly we will integrate this to 0 to some no formation which we need to which we need it. Okay, so let me write no dash. Okay, this is the no concentration which will be at the end of the combustor. So let's say if I differentiate it no dash. Now this Kg, N2, O2, all this can depend on time. So Kg is going to depend on only temperature, and with temperature, the time temperature is not going to change. The adiabatic flame temperature is going to reach or little less than adiabatic flame temperature, but more or less the combustor is going to be at same temperature, at a very high temperature. So temperature is not going to be a function of time. So you can take Kg to be constant, and N2 and O2 is we know combustion is going to happen. So N2 and O2 is going to be present, and the formation of NO is parts per million. We are calculating for a parts per million, right? So uh, it is very less compared to the N2 and O2 concentration. So the amount of N2 and O2 is going to change for forming NO is going to be very less. So we can take another assumption that N2 and O2's concentrations are constant. So assuming that also, we can simply arrive at an upper estimate to find out which is the right thing. I will at the end of the class I will also tell what they really do nowadays. Okay, so um, we are doing a lot of approximations here, right? So each approximation can lead to different results. So how nowadays people are finding it out without doing this approximation, we will discuss this at the end of the class. So before that, so this is how your NO formation is going to look like. What we need to do is tau residual is known, which we know. Only thing is find. So to find NO dash, which is actually NO dash is nothing but NO at time t is equal to tau residual. Sorry, not residual, it's residence. Sorry about that. Tau residence is nothing but NO dash. So both are same. Um, to find NO, we need value for Kg, which is a function of temperature. So we need temperature, we need N2 concentration, we need O2 concentration. Okay, so only these are the things it's going to depend on. So how do we find this temperature N2 and O2 concentration? Temperature is going to be the result of this combustion reaction. This whole combustion reaction is going to be result. The temperature is going to be a result of this reaction. So which means if this is firing, then I will convert all these things into this, and then I will find the temperature. So let's say you can find adiabatic flame temperature by equating the enthalpy of the reactants is equal to enthalpy of products. And temperature it reach is what we will use it here. And similarly, N2 and O2 we need to find out. So that is why we are going to take help of NASA CEA to find out this. So we already uh, discussed how do we do in NASA CA in the last class. If you missed it, please go through the recordings available. So I will show you the today also I will show you the demo. No need to worry. So we need to find use this for NASA CA, and all these are going to be a function of. So all these are going to be a function of a different equivalence ratio. So for a different equivalence ratio, these are also going to change. Okay, and so for convenience, let's rewrite this equation. This is, let's say, equation 3 in terms of mole fraction, because NASA CA will give us mole fraction, so we can directly substitute it. rewrite 3. Okay, so that you can write it as x of no dash, so going to be kg times x of n2 x of O2 power of tau residence square root of p by RUT. So basically you need to put p by multiply this for p by RUT per n2. So this is nothing but x of no. This is equivalent. So and then x of O2 into p by RUT whole power of, right? So this and this gets cancelled and only this p by RUT will be additionally present in this equation. So that is what we have here. And the mole fractions can simply get converted into parts per million by volume. Okay, so that is the reason it is convenient to use this setup. So now we have to choose a equivalence ratio for which the NOx emission will be less. So for that we need to find which equivalence ratio. For each and every equivalence ratio we need to find. Let's say we will put a table. We will draw a table here. So for an equivalence ratio 5, okay, we will find what is the uh, mole fraction of N2, fraction of O2. This is based on equilibrium. Okay, and then we will also find what is, now we will find mole fraction of NO dash from the Zeldovich mechanism, right? In between we need to find the mole temperature also, right? So phi T adiabatic, okay, and then Zeldovich mechanism. So this is going to tell us which phi we need to choose. So how can we write? Let's say we will change our phi from 0.5, okay, uh, 0.8, let's say till here. Okay, let's see whether this is going to tell us or not. So let's run our simulation for let's run NASA CEA to find T adiabatic X N2 and O2. Okay, so let me present from here. Present share. Share. So um, okay, so I think it is getting shared. All right. So here we have CEA. Now let me zoom it out. And we are going to use assigned enthalpy and pressure, which we discussed already. And this is just some numbers. So for pressure, we are going to have 1 atmospheric pressure. Okay, so 1 atmospheric pressure we selected, and then the fuel is going to be um, propane C3H8. So let's use periodic table, nitrogen and carbon. Okay, and now we have C3H8 as a propane. So this is there, and accept it 100%. It's going to be only one fuel we have, and the temperature is going to be at standard atmospheric temperature. Let's say from 298, let's say you are doing it, and I'm going to use air, so that is fine. Oxidizer temperature is also, it's what was that, 298 Kelvin, and then so pure air, and I need to give is a fuel ratio, equivalence ratio. Equivalence ratio is going to use zero point 0.5. What are the things we have? Zero point 0.8, and we have 1, we have 1.2, then we have 1.5. Okay, so I gave a 5 equivalence ratio for which I want to find out. Going to the next. Now we have we are interested in mole fraction because that is what we are going to put it in our equations. So, and then let's perform CE analysis. So this is an equilibrium analysis. This will also, so let's have a look at it. So we have propane, we have air here, and then we have its formation enthalpy, or the enthalpy at temperature 298. We have formation enthalpy. We have some temperature here, and also we have mole fractions here. Now you should ask that, say, I already have NO concentrations here also. In addition, I have OH, O2. So this may not be the right estimate, right? So we need to have only uh, CO2, H2O, O2, O and N2. So maybe you can take this as an approximation, but let's try different. Let's see. Let's let's see if we can omit those additional species. Okay. So select species, omit only and insert. So I have a lot of species here. So let's say if I omit I omit H, I omit H2, I omit what's the other one? Huh. O2 I will keep, O I will keep, because those two I require, and NO2, NO3 will, for now we will omit it, OH also we will omit it. Okay. And NO also we will omit it because we are going to find NO, how much NO. So let's say for this, let's perform the analysis. Let's see whether it works. Okay, it worked. So here we have only argon, CO2, H2O, N2 and O2. So which is good. So these are the only mole fractions present. So basically what we did was we tried to, for we are considering only CO2, H2O, N2 and O2, in addition O also, but we added, but it looks like it is very less, so they omitted it. Uh, but we are going to consider only these species, so we tweaked the program to show us only or to perform the equilibrium calculation only for those species. So it is same like I am calculating myself using a separate program. So this NASA CA is also giving the same results. Okay, so now for equivalence ratio of 5, I have a temperature of this. Let me quickly take down these values so that so for equivalence ratio of 5, I have adiabatic flame temperature to be 1509 kelvins. Okay, 0 Kelvin. And this is all in terms of Kelvin. Um, that the mole fraction of N2 is 0.75 and mole fraction of O2 is zero point 0.1. And now let's go down. We have zero point 0.8. For zero point 0.8, mole fraction of N2 is zero point 0.8. First temperature is 2057 Kelvin. N2 is 0.73 and O2 is 0.039. Okay, and let's go down. Then we have 96 Kelvin at equivalence ratio of 1. For that we have N2 is 0.715 and O2 is 0.067, sorry, 0067, 067, or you can simply write 007. That is also fine. We're also seeing additional species because we didn't omit CO, so it is coming there, but we no need to worry about it. And now we have equivalence ratio of 1.2. For 1.2 we have 1200 Kelvin. You can see that the maximum reached around 1. Actually it will reach close to equivalence ratio of 1. It will not be exactly 1. So whether in fuel lean or fuel rich, it's going to be less than the flame temperature, to be less than the stoichiometric mixture. Okay. So 1.2 N2 is going to be 0.683468, and O2 is very less, 2 into 10 power minus 5, which is good. Now going down we have 1.5. 1.5 N2 is temperature is 1965 Kelvin, and is 0.64, and O2 is gone. O2 is not present. Interesting, O2 is not present. So maybe you shouldn't. Let's ignore 1.5 and let's see for the four values. Okay. So now I have to find. Let me present it from here. I have written down all the things. So here I have written down all the right. So here I have written down all the values, N2 and O2 mole fractions, flame temperatures, and everything. Now we need to fill this column of NO dash. So what we could do is we could uh, either what we could do is we could do all the calculation by ourselves using this. But what I'm going to do is I'm going to do something different. What I will do is maybe I will use MATLAB or something to calculate this. So let me share that also. So share now. I will share the whole window now. Okay. I think I share the whole window. So let's say if I go to this, you should be able to. So right. So there is this. We have command window. So I think you all know how to do it. But let me just quickly calculate it here. So what I found was I have 5 equivalence ratio, which is 0.5, 0.8, 1, 1.2 and 1.5. You can do this in uh, your cells also. So and then T adiabatic is actually 1510 2057 2296 2200 1965. Okay, and xn2. So this is the mole fraction of nitrogen, that is 0.75, 0.73, 0.715, 0.68, 0.64. Okay, and mole fraction of O2. Mole fraction of O2 is 0.1, 0.039, 0.007, and 2e minus 5. And okay, last one is not known. So let's say I write it 1e minus 6 for now, but we can just ignore it. For that we need to, so let's find kg. What is kg? Kg is nothing but kg we found it's going to be 2 into k1 half. So let me write it out like so inverse so, okay, and we have what do we have? We need to find rates. First let's find rates. Rates is, first is k1f. K1f is going to be 1.8. It is given in the question. 1.82 into 10 power 14 times exponential of how much is that? Minus 38370 divided by T adiabatic. So okay, so T adiabatic is what? So we will get a lot of K1s as our rate, so that is also fine for us. And then we have K2F. We no need to find because K2F in that nothing is dependent on K2F. And then we have kgs. Kg is 2 times K1F times Kp. We need to find Kp also times. So since it's an array, we have to do dot processing. Kp times pressure divided by Ru T adiabatic. Ru and P also. So P is 101325. Ru is going to be what is Ru? 8314.5. Let's write it in terms of joules per mole Kelvin. Okay, so joules per mole is how much is that? So this is, yeah, 8314 is what joules per mole Kelvin is. Let me write it down here also. Joules per mole Kelvin. And these, I think it is in terms of centimeter cube, if I'm right. It's a centimeter cube per mole second. Right? So let's say if since it's in centimeter cube, I may need to multiply it by 10 meter cube. If I want to convert, I need to multiply it by minus 6. Okay, and T adiabatic is in terms of Kelvin, P is in terms of Pascal, so no problem. And then kg is there. Kg So you find kg, are you tau residence is equal to 10 milliseconds, right? So 10 into 10 power minus 3. This is the residence time. Now we need to find NOx, NO uh, concentration. NO concentration we already know, XNO is equal to kg times N2 times XO2 power of, so maybe okay, power of, or you can simply write 0.5. So 2 power 0.5, and then multiplied by tau residence times square root of P by RU times T by T. Okay, this is also going to be array, so there should be dots everywhere. Okay, this is the tau. Let's say if I run this, there is some error over here. Okay, there is no kp actually. Okay, now we need to define kp also. Kp, we found out that it's going to be exponential of minus delta g by u t adiabatic, right? So then we need to know what is delta g. Delta G is nothing but 2 times formation enthalpy. Formation gives free energy of O, and that is actually a function of temperature. So since your temperature increases, that also should change. So but for now what we will do, we will assume that it is constant, or we will take a most like good estimate for it. So I am looking at the formation enthalpy of oxygen is going to be around so let's say it's 12170 kilojoules per kilomole, which means joules per mole. So 121,709. Okay, so if this is the delta G, so what is my NOx emission? Let's try to find out. So there is one more issue of kg over here. Okay, so this string doesn't match. Okay, all right, so we got NO emissions over here. So X and O. So let's say if I write it down, let me quickly write this also down. So everything is in terms of minus 5. So it's 0.0006 into 10 power minus 5. Okay, that is for equivalence ratio 0.5. and we have 1 to 10 power minus 5, and we have 0.45 5, and then we have 0.012 into 10 power. So let's say if I want to write in terms of parts per million, okay, let me stop here and okay, so let me stop presenting over here and I will come back to okay. So now let's say if I want to write it in terms of parts per million, you just need to multiply by 10 power 6 here. So x in O2 in parts per million by volume. So this is going to be around 60. This is going to be around sorry, it is not 60, uh, 0.006, and this is going to be around 1.869. This is going to be around 4.592. This is going to be around 0.12, 0.012. Okay, so this is the parts per million. Um, this is the amount of NOx formation. So if we look at it, maybe you can go through the calculation once again if you so, but this is the way how we need to derive it. So if we look at it based on our observation currently, we see that all the XNO are less than 30 parts per million by volume. Okay, so you can use any of the equivalence ratio. You also should note that you have temperatures of this range. So temperatures ranging from 500 to 2296. Okay, this is the temperature range we have. So we do not need economically, if you look at it economically, to have more fuel. We don't want more fuel more fuel to be used, which means 5 greater than 1 is not the right choice. So we do not want the equivalence ratio to be above 1. So if you want equivalence ratio to be below 1, then you should look at only uh, these values. So if you look at these values are well within the range. Like NO formation is very less. So let's say if I select phi is equal to zero point 0.5, then my T adiabatic is going to be 1500 Kelvin, and my NOx emission is also less than 30 parts per million. Now, if this so from emission guidelines, this is working from emission guidelines. So phi equal to zero point 0.5 works. Okay. Now you need to check other parameters. The other parameters include the flame temperatures. So since the gases are exposed to turbine, the turbine will be facing very high temperatures. So at the present state of art is you cannot have turbine blade above 1600 Kelvin or 1800 Kelvin. So if you are motivated in that range, okay, then uh, considering considering the technology turbine blade, T should be less than, let's say, 1600 Kelvin. So the ideal choice would be to go with equivalence ratio of 0.5, because it is also economically efficient, because you're running your whole combustor in a lean mixture, and also you are meeting the turbine conditions, so you have to meet turbine conditions. And this has a negative effect also. The reason is, since you have less temperature, you are going to have less output, which means you are going to thrust from the engine, but you cannot do anything about it. So if you go above, NOx emission gets violated, turbine blade temperature violated. Because of that, other problems will be created. Instead of that, it's better to go with lean conditions, economically efficient also, uh, but performance wise it will get affected, that is true. So uh, if you may need to reconsider this calculations also. Mostly at this point of time, it should actually violate um, the what do you call, for some reason we are not getting it. So probably my delta G is wrong. Maybe let me try G. So yeah. So if you have a closer look, then you may be able to find the problem. All right. So that is how you find the NOx emission in any of the in any systems. You can even find the carbon monoxide, how much is it coming out, based on this kind of calculations. Uh, but basically nowadays people no need to use this steady state. So we use steady state approximation. We used partial elimination, partial equilibrium approximation, and we ended up arriving at the NOx emissions. Right. So nowadays people no need to do that approximation. People can do really high fidelity CFD calculations uh, to find out what would be my temperature at the exit of the combustor, what would be the um, exact NOx emission or NOx formation, how much is it forming exactly, you can calculate it. To calculate it, you need to have a very good computational framework and also good computational resources. So basically, you need to model the whole combustion. You need to model the each and every reaction mechanism. You need to take care of mass, momentum, and energy conservation. And in addition to this, uh, species mass conservation has to be taken care. So because each and every species is going to get involved, each and every species will get consumed, which will get destructed, will get produced. So species mass fraction equation and the construction destruction will be taken care by the chemical source terms, which comes from mechanism, and mass and momentum conservation you need to take care. So these laws which you need to follow, which you need to solve, these equations which you need to solve in order to end up arriving at these more accurate results, more accurate um, capturing of these mechanisms, you'll be taught in coming week. Okay, so you will be taught what is the you know conservation laws, for example, for this kind of systems. So basically, we already know it's a mass, momentum, and energy conservation, and in addition, species conservation is going to come. So you need to solve this kind of full set of equations in order to find the more accurate results. So nowadays, people don't do. People directly do CFD because of improvement in our technology, improvement in computers. But back in 80s, let's say back in 90s, 30 years from now, or 40 years from now, we do not have that powerful computers, but so we need to rely on such analytical results, analytical you need to apply such approximations in order to arrive at more better estimate of any uh, you know uh, concentration of any species. So that is how it's been done. So that is why I want to show you how we can, by simple hand calculation or by simple, without using such high fidelity CFD softwares, without using very high computing resources, we can come up with a good estimate by applying such mechanism. By applying this way of doing this. So that is what I want to show you today. And if you have any doubts regarding this, if you want to discuss further, you can come to next class and we can have a discussion, or you can even post your questions in the discussion forum. Okay. So with this, I will stop this class. See you in the next class.